Hello friends, welcome to engineering tutorial. In my previous video, we discussed about some of the basic concepts related to angle modulation, the types of angle modulation, and we also covered some basic concepts related to frequency modulation and the formation of frequency modulated signal waveform. So in today's video we will be discussing about some more concepts related to a frequency modulated signal such as frequency deviation, modulation index and bandwidth of a frequency modulated signal. So let's get started. So the first concept which we are going to study is frequency deviation. So what is frequency deviation? So it is the maximum change in the instantaneous frequency of the carrier signal, which is change occurs when the carrier signal from the carrier frequency, or in other words it can also be defined as the maximum departure of the instantaneous frequency omega subscript I from the carrier frequency omega c. The departure occurs because in frequency modulation the change occurs proportional to the message signal. The carrier frequency is altered proportional to the message signal. So the maximum change, the maximum frequency change that can happen, it is given by the frequency deviation. In mathematical terms, frequency deviation is given by delta omega equals to omega subscript I minus omega subscript c modulus max, the maximum change. So it can be further written as the instantaneous frequency. We know that it is given by omega c plus kfmt, which is the frequency modulation process as we discussed in the previous video. This term is the frequency modulation. So the frequency modulation, the change in frequency which has been done to the carrier wave. Now the carrier frequency when subtracted from it gives us the frequency deviation. This is the maximum change that can happen in the carrier frequency because of the message signal. This is the change that happens. KFMT is the change that happens to the carrier frequency. So when we subtract the carrier frequency from it, we get the change that has happened to the carrier signal as a result of frequency modulation. So that gives us KFMT modulus max. Now MT is the message signal which is given by EM cos omega MT, a cosine signal. For simpler analysis, we always take cosine signal. So the maximum value of cos is 1, which happens at omega mt is equal to 0 degree. So the maximum value of frequency deviation is given by kf into em, that is the proportionality factor in frequency modulation into the amplitude of the message signal. The product of these two terms gives us the value of frequency deviation. Now the proportionality factor can be expressed in two ways. That is delta omega by em when omega is taken in radians, unit is radian per volt, and when it is taken in hertz, it is given by delta f by em hertz per volt. Okay, so this is the concept of frequency deviation, which is the maximum change in frequency which happens in the carrier signal wave or the carrier frequency because of the message signal. Okay, next is modulation index. Modulation index in frequency modulation. So in frequency modulation, modulation index defines the efficiency of modulation and is given by the ratio between the frequency deviation and the modulating signal frequency. It is the ratio between the frequency deviation and the modulation signal frequency. which is given by kfem, which is the frequency deviation value, divided by omega m, which is the angular frequency of the message or modulating signal. Now it can also be written as delta f by fm, which is equal to kfem by fm when frequency is represented in hertz. Here the frequency is represented in radians per second. Now this is modulation index is also denoted by beta in case of frequency modulation. Now in standard frequency modulation, the value of modulation index or beta is always much greater than 1. Well, in amplitude modulation, the modulation index value 100% efficiency was never achieved, was lesser than 1. So in modulation, in frequency modulation is greater than 1. So this is the modulation index formula for a frequency modulated signal, which is the ratio between the frequency deviation and the modulating signal frequency. Next is the representation of a frequency modulated signal waveform in terms of modulation index or beta. So we know that we represent a frequency modulated signal in this way, that is EC cos omega ct plus kf integration of mt dt, which we discussed in the first video related to frequency modulation, where we derived the mathematical expression for a frequency modulated signal. You can check out that video. Now when we substitute mt with em cos omega mt and perform integration in it, we get the value as EC cos omega ct plus kf em by omega m sin omega mt. Now this value kf em by omega m is the value of modulation index, which is the ratio between the frequency deviation kf em by the modulating signal frequency, which we just studied in the previous paper. So now we can write this frequency modulated signal as EFMT is equal to EC cos omega ct plus beta sin omega mt. So this is the representation of a frequency modulated signal in terms of the modulation index beta. Beta is kfem by omega m, which is the modulation index. So this is one form of representation of a frequency modulated signal. Now in analog communication, both the message and the carrier signal can be taken sine or cosine. There should be no confusion related to that. Only for simpler calculations, for simpler analysis, we take the cosine wave, because if you would have taken sine wave, if we would have performed integration here of sine, we would have got a negative sign. So to avoid that, we take a cosine signal, so that when we perform integration, we get a sine and a positive sign. So you can take sine signal, you can take cosine signal, there is no problem. There should be no confusion related to that. The carrier signal can be in sine form, it can be in cosine form. The message signal, it can be in sine form or cosine form. There is no problem with that. So here are the different ways in which the frequency modulated signal can be represented. So when you take the message signal, there are 4 combinations. There are many combinations that can be formed when you take the message signal as sine and the carrier signal as cosine, or when you take the message signal as cosine and the carrier signal as sine, when you take both cosine, when you take both sine. So there will be many combinations that will be formed. So here are some of the standard representations of the frequency modulated signal. Now this representation is when both the message and the carrier signals are in cosine form. Okay, so this is the basic representation of frequency modulated signal in terms of modulation index. Next is the bandwidth of a frequency modulated signal, or bandwidth in frequency modulation. Now, the number of sidebands which occur in frequency modulation is very high as compared to that in amplitude modulation, where there is only two sidebands, the upper and lower sideband. But in frequency modulation, the number of sidebands are very high. So it is very difficult to calculate the bandwidth. So in general, in frequency modulation, the bandwidth, the formula for bandwidth is given by Carson's rule. This rule is used to calculate the bandwidth in frequency modulation. So what is the value of, or the formula for bandwidth? Now, as per Carson's rule, the bandwidth in frequency modulation is twice the sum of frequency deviation delta f plus the modulating or the message signal frequency fm. Okay, it is twice the sum of the frequency deviation and the modulating signal frequency. Bandwidth is equal to 2 into delta f plus fm. So it can also be written as, when you take fm outside and take fm common, so it is given by 2fm into delta f by fm plus 1. Now delta f by fm, we all know, is the modulation index beta. So it can also be written as 2fm into beta plus 1. Now here, some of the things that are associated with it are, the total number of sidebands is beta plus 1. Now as I said, the value of beta or modulation index in frequency modulation is much greater than 1. So the number of sidebands will be much greater than 1 as compared to amplitude modulation, in which the number of sidebands were only 2, the upper and lower sidebands. So the number of sidebands in frequency modulation is high as compared to amplitude modulation. For the first sideband, the bandwidth is given by 2fm, or twice the message signal frequency. For the second sideband, the bandwidth is equal to 2 into 2fm, which is equal to 4fm, which is 4 times of the message signal frequency. So this general formula for the nth sideband, the bandwidth of the nth sideband is n into 2fm, where fm is the modulating signal frequency. So here the bandwidth in frequency modulation is very high, as the number of sidebands are high in frequency modulation as compared to that in amplitude modulation. So here we have discussed the concepts such as frequency deviation, modulation index and bandwidth in frequency modulation. In my next video, I'll be discussing about the spectrum of signals which occur in frequency modulation, and we will also represent the sidebands in that frequency modulated signal spectrum. And we'll discuss some other concepts also. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.